Alright guys, so here we have a piston cylinder assembly. So here we have a piston over here with a mass of 50 kilograms, and it's going to be acting with a gravity of 9.81 meters per second squared. Now above this piston we do have atmospheric pressure of 100 kilopascals, and below this piston we have a tenth of a kilogram of water, and it's at 100 degrees Celsius. We're also given the area of this entire, piston or inner cylinder, if you want to call it, of 0.01 meters squared. Now, because this piston can slide up and down, that means that it's going to be inducing a pressure on this water because obviously the weight of that piston is going to be going down, and at the same time you have pressure pushing down on that piston into the water. So we're tasked to find the pressure that's induced on the water here by both the piston and the atmospheric pressure, and then we're also going to be looking for the volume of this water in cubic centimeters. Alright, so to find the pressure that's acting on the water, this isn't really too much thermo, but more so statics for this part of the problem. So basically, if you just do the sum of the forces in the y direction, that's how you get the total added pressure, or the added force on this water. So if we have the pressure of the water equals the atmospheric pressure, because obviously that atmospheric pressure is going to be pushing down on the piston, right? And then, so we'll have 100 kilopascals. And then to that, we're going to have to add basically the weight of this piston, because this piston's also going to be pushing down. And with what pressure? Well, if you recall that pressure equals force divided by area, we can just add the force divided by area. So we'll have the force divided by area. Now to find that force divided by area, the force is simply going to be the mass times acceleration divided by the area which is given to us. So we can plug in what we have, and we have 50 kilograms times 9.81 meters per second squared, and we're going to divide that by 0.01 meters squared, and so this is going to give us 49,050. And what's the unit? Well, if we have a kilogram meter per second squared on the top and a meter squared on the bottom, well, the top awfully looks like a Newton because it's just mass times acceleration, which is what a Newton is. Divide that by the area of meters squared, and that's going to yield you with a Pascal. So we have 49,050 pascals. So now if we just take the summation of the atmospheric pressure and the pressure induced by the piston, we'll have that the pressure, P equals 100 kilopascals, plus this pressure here is going to be equal to, probably just draw an arrow to it, so that's going to be 49.05 kilopascals. You just divide by 1,000, and so we're going to add 49.05 kilopascals, and your total pressure equals 149.05 kilopascals. So next we have to find the volume. So to find the volume, if you recall, we'll do some thermo here. The specific volume equals the total volume divided by the mass, right? So if you rearrange this, you'll be able to find that the volume equals the specific volume times the mass. Now we already have the mass right over here, 0.1 kilograms, but we're looking for the specific volume now. So to find the specific volume, we know that we have a temperature at 100 degrees Celsius, and we have a pressure at 149.05 kilopascals, right? So using these two, we should be able to find the specific volume. So we're going to have to retrieve that specific volume from the property table, but to know which property table I'm going to be using, I'm going to go ahead and draw a vapor dome here. So we'll just draw a generic dome like that. And then I'm going to use that the temperature is constant. So basically along this line here, anywhere on that line is 100 degrees Celsius. And on the y-axis, we're going to have the pressure. And on the x-axis, we're going to have the specific volume. Now, along this horizontal is where the phase change happens. This is where your pressure is saturated. So this is your Psat. And we're going to have to retrieve what that is for 100 degrees Celsius. But in the meantime, here on the left is going to be your saturated liquid, and here is going to be your saturated vapor. So essentially what I'm getting at is, if our 149.05 kilopascals is greater than the Psat, then we'll be somewhere over here. and will be in the liquid region. Now, if our 149.05 is greater than Pset, then we would be over here instead, and then we'd be in the superheated region, right? Because we have to be along this line. And now if we're somewhere between VF and VG, essentially right over here, then we would have a two-phase mixture. But for now, let's turn to our property table. So if we go to table A2, which is the saturated water temperatures or saturated water tables for liquid water, and if we go to 100 degrees Celsius, we have a pressure of 1.014 bar. Now, all you have to do is multiply by 10 squared. You have your conversion factors right over here in the corner, and you'll have that this equals 101.4 kilopascals. So what I'm going to do is I'm going to replace this Psat with 101.4, and that's kilopascals. Now, we were given not only atmospheric pressure of 100 kilopascals, but also an induced pressure of 49.05 kilopascals. So we have a total of 149, which would be higher than this 101. So we'd probably be somewhere over here. That'd be 149.05 kPa. And so you're over here. And if you're over here, well, then here's your V. You'd use, let's just call this V, and this is your specific volume given our exact parameters. Now, I'm going to approximate that our specific volume of our compressed liquid is very close in value to our specific volume of a saturated liquid, right? So what this allows me to do is it allows me to pull the saturated liquid specific volume of 100 degrees Fahrenheit. So essentially this value right here. 1.01435 times 10 to the negative third, because you have to divide by 1,000. So our specific volume is 1.0435 times 10 to the negative third, and that's in M3 per kg. And now all we have to do is plug in chug. So we'll have that our total volume equals 1.0435 times 10 to the negative third, M3 per kg, times your mass of 0.1 kilograms, and your kilograms and kilograms cancel out, and you can just increase or decrease your exponent here to equal 1.0435 times 10 to the negative fourth, and that's going to be in M3. However, the problem did ask for cubic centimeters, so all you have to do is multiply by 100 squared, or 100 cubed, sorry, and you'll have that the total volume equals 104.35 cubic centimeters.